Good afternoon. This is presented by Group 4 from Andy and Yuhao. The figure on the left shows the reference design that was assigned to the group, and on the right is our CAD model designed using NX. So this is a detailed drawing for the light-weighted design structure. To reduce the weight, we decided to decrease the thickness of the frame tube, and in the fork, the top solid bar is half hollowed. To read online, we found that Reynolds 953 steel tube has the highest strength and stiffness compared to other steel we found. We will be presenting 3 scenarios, which we will explain in the later detail slides. For scenario 1, we have a person weight 65 kilograms sitting on a bicycle and hands on the handle while the bicycle is in rest, with a loading condition showing in the figures on the right. From NSYS, we obtained a total deformation of 0.17 mm and a stress of 59.8 megapascal. For fatigue, we have the safety factor at 1.441 for scenario 1. For scenario 2, we have a person weight 65 kilograms riding on the bicycle with a speed of 10 km per hour. Assuming the bicycle got hit in the front wheel, the impact force is to be 262 newtons, calculated using Newton's first law. The total deformation is 25.157 millimeters, an equivalent stress of 527 megapascal. A safety factor of 0.16. For scenario 3, we have a person weight 65 kilograms sitting on the bicycle got hit by an object in the back wheel at a speed of 15 kilometers per hour. The impact force is 362 newtons, calculated using total deformation is 93.4 millimeter and a stress at 1092 megapascal for scenario 3. Safety factor for fatigue is at 0.07894.
For moderate weight, we increase all the tube thickness and the joint for the frame. And for the fork, we have increased the width and thickness at the bracket, shown in the figures. We apply the same load conditions for the same scenarios. So for scenario 1, the total deformation is 0.035 millimeters, and the stress is 25.8 megapascal. The safety factor for fatigue is 3.337. So for scenario 2, the total deformation is 17.2 millimeters, and the equivalent stress is 244.08 megapascal. The safety factor for fatigue is 0.353. For scenario 3, the total deformation is 84.8 millimeters, and the equivalent stress is 1887.8 megapascal. The safety factor of the fatigue is 0.045.
Next, we have considered aluminum as our alternatives. The most common aluminum alloy used is 6061 and 7005, but we have decided to use 6061 because it is easier to handle and it's cheaper and lightweight. The key properties of 6061 are shown in the slide.
For aluminum, we still consider the same load conditions. For scenario 1, the total deformation is 0.098 millimeters, and the equivalent stress is 25.84 megapascal. The safety factor for fatigue is 3.20. For scenario 2, the total deformation is 48.43 millimeters, and the equivalent stress is 244.13 megapascal. The safety factor of fatigue is 0.338. For scenario 3, the total deformation is 240.31 millimeters, and the equivalent stress is 1884.7 megapascal. The safety factor of fatigue is 0.043.
Overall results are shown in the table.